Okay, so this is just a little introduction to the projectile motion lab. So what we want to do is we want to measure the initial speed of the ball coming out of this projectile launcher. And we're going to do it 5 different ways. Now, and the projectile launcher is always going to have the same setting. So you would think, in an ideal world, we're measuring the same thing. The launcher has the same setting. We're just doing it 5 different ways. So in an ideal world, we should get the same results, right? Well, this is not an ideal world, and we're going to get different results because each of the methods, each of the 5 different methods, we're going to use different measurements and different pieces of equipment. And so we're going to get different uncertainties, so that's why we're going to get different results. All right, here's an example. So for part 1A, this is the equation we're going to use to calculate the V0. And you can see that it depends on the delta x. All right, on the other hand, for 1B, there's no delta x anymore. There's a delta y. And so again, we're just using different measurements for each different method. And delta x is going to have different errors than delta y. For part 2, we're going to have to measure delta x and delta y. And so again, we should expect different results since we're using different measurements. Now, before I get into the specifics, oh, by the way, you want to pay attention to this video because some of the questions that are asked on the lab handout are going to be answered in this video. So pay attention. So before I get into all of the different specifics on the different methods, I need to talk about something called a photo gate. Now, this better look familiar. So this is the lab, this is lab 3, free fall. And these 2 things are called photo gates. And let me just read something from the lab 3, or from the free fall lab handout. This is what I wrote. So we're studying the time in the air, which is called the time of flight, versus the initial speed. So this is what it says on the handout. When the ball passes through the first photo gate, 2 clocks in the computer are turned on. When the ball passes through the second photo gate, the first clock is turned off. All right, so here's the question. Why does a clock in the computer turn off or on as the balls pass through the photo gate? In other words, what I'm really saying is, how does this crazy thing work? So here's a picture of a photo gate, and here's how it works. So you can't see it, but there's actually a beam of light from here to here. And it's infrared light. It's not visible light, it's infrared light, so we can't see it. Now, when an object goes through this, right, like a ball goes through this, it breaks the beam. And whenever the beam is broken, it sends a signal to the computer. For example, it can turn the clock on, or it can turn the clock off. There's many, many different ways to set this up, and I'll discuss some more of that later. All right, so now let's go back to our projectile motion lab and talk about these 5 different methods we're going to use to figure out V0. Okay, so this is part 1. Now, in part 1, as I just showed you a few minutes ago, we need to measure delta x as well as delta y. Well, in order to do that, we need to know the final position and the initial position and the final position. So let me talk about the final position because that's the easy one. So the final position, we're going to use what's called carbon paper. This is a relic of the past. So you can see that this is the time of flight pad that you're familiar with. And so just pretend there's a time of flight pad here. Then we put down a piece of white paper. Then we put the carbon paper on top. So what happens is the ball hits the carbon paper. So let me show you what happens. Okay, So see what happens? So when the ball hits the carbon paper, it leaves an imprint. Okay, so I guess what I'm saying is it's pretty, we're going to know exactly where the ball is, right? Because of the imprint from the carbon paper. Okay, so we'll know the final position, right? X final, Y final. Piece of cake. Now here's the problem though. What's the initial position? Well, the initial position is when the ball passes through the photo gate's light beam. Okay, well where's that? Well, it's in midair, right? It's in midair. Okay, so, I mean, it's kind of hard to tell exactly where it is. And so all I'm saying is, if we don't know, we just have to estimate. And so if we have to estimate the initial position, that means that our delta y is going to have some uncertainty, and our delta x is going to have some uncertainty. Okay? All right. Okay, let's talk about part 2. Now here, there's no photo gate, right? And so what's the initial position here? The initial position is when the ball, so there's a spring inside this. The initial position is when the ball leaves the spring. And it's right there. It's labeled on the photo gate. Now you can't see that, I know. There, right? So it says right there, launch position of the ball. Okay, so, it's pretty simple then to figure out the initial position. And again, it's simple to figure out the final position. Let me show you something. So, again, this is the initial position. So how do we find the position on the table? Well, it's actually pretty simple. So this is called a Plumb Bob. You actually use it when you build houses. And so you know where the initial position is. Here, let me show it here. Let's say that this is the initial position right here. So you just drop this down, and then it's perfectly vertical. All right. Okay, so all I'm trying to say is that this is simple to measure, right? You know where that is. You can measure the delta y. Use your Plumb Bob to put a dot right there. Then you can measure this. Piece of cake. So this one, there's not so much uncertainty as in part 1. Because it's easy for this one to measure the delta y and the delta x. Because we know exactly where the initial position is and where the final position is. We don't have to guess like we did for this guy. Okay, so let's talk about part 3. Okay, so look, this is part 3. Look, all we have is a photo gate, which is connected to a timer, and we have a caliper. Now, what's a caliper? So a caliper is a device that's used to measure things very, very accurately. For example, if you wanted to measure the thickness of a piece of paper, how could you do that with a meter stick? You can't. But with this, you just go like that, and you can get the measurement. So what we need for part 3 is we need the diameter of the ball. So you just put it in here, and you just measure it. And you can get really, really great accuracy. It's kind of it's 1 inch, 2.54 centimeters. Okay, so we use the caliper to measure the diameter of the ball. But now we're going to use the photo gate in a completely different way. What's going to happen here is, okay, so here's the light beam, just pretend, right? And just say the ball is going in this direction. Okay, so we're going to set up the photo gate and a timer in a new way. In this method, as soon as the ball crosses that light beam, the clock is going to turn on, and it's going to stay on. Okay, the ball keeps moving, right? And then, as soon as the ball, as soon as this part leaves the light beam, it's going to turn off. So in other words, we're measuring how much time it takes for the ball to cross the light beam. Okay, great. And then, you know, we've measured the diameter with the caliper. We just measured the time for the ball to cross the light beam with the photo gate. So the initial speed is just the diameter over the time. Piece of cake. It works great, right? Well, maybe. Okay, so here's a problem. Here's the huge problem. Okay, now, sorry, I have to shift. So here, you know, we're saying that the ball is going this way. Now let's shift it. Sorry. Let's say that the ball is going this way. All right. So for this method to work, the ball, I mean the entire diameter of the ball has to pass through the light beam. Right? That's what, because again, because we're saying the speed is the diameter, 2.54 centimeters, divided by the time. Well, what if the projectile launcher doesn't shoot things straight? What if it shoots a little bit to the right or to the left of that photo gate light beam? In other words, let's say it does that. So now the ball is kind of going to the right a little bit. Well, now only this part of the ball is passing through the light beam. Now we don't know that because we can't see it, right? And I mean, our formula says 2.54 centimeters, the diameter, over the time. Well, if only this part goes through the light beam, then you know, it's not going to take as much time, right, as it should. And since velocity is distance over time, if the time is too short, what's going to happen to the speed? It's going to be too high. So, oh boy, right? And again, we're never going to know, you know, because we can't see it. So the only way to really see if this problem occurs is to look at the results. If the velocities for this method are all higher than everything else, well, you know that this is what happened. Okay, the fourth part. By the way, there's 2 methods in part 1. That's why there's really 5 methods. Okay, this is part 4. Part 4, it looks a little bit like what you did in the free fall lab, right? For part 4, you know the ball comes out here, right? So clock turns off, clock turns on. And you measure this distance. It's 10 centimeters. It's made that way to be super accurate. So you know the distance very accurately, 10 centimeters. You know the time very accurately. So the velocity is the distance over time. Bingo. So there's not a whole lot that can go wrong there, right? So all I'm saying is, you know, again, 5 different methods, 5 different measurements, 5 different pieces of equipment. And so you're going to get some uncertainty. And it's important that you realize that. All righty, thank you.